Good afternoon, everybody, and welcome to the final SAGTA webinar for 2025. And just as I'm saying that, I cannot believe we're at the end of the 2025 academic year. And I would just like to say thank you to all of our members who have joined us today, as well as those of you who are not part of SAGTA. But I know it is a very busy time of the year. You are busy marking and trying to get the final assessments done. But today we have a very interesting webinar taking place, and I do hope you enjoy. And throughout the course of this year, we have had a few great webinars. And I'd just like to refresh that if you have missed any of our webinars, you can go to the SAGTA YouTube page and go catch any of our recordings. We've had phenomenal webinars from people such as John Roth, who did the exciting rock stories. We've had a webinar on drone farming, space storms in Southern Africa, the map downloader, and we're ending the year with a very interesting topic and very topical at the moment, definitely on the La Nina influence on Southern Africa and definitely in Africa. So just a little bit of housekeeping. Please can I ask everybody to make sure that your microphones are off and that your cameras are not on, just so that it helps with the bandwidth for the webinar today. So just starting off, just to remind everybody that this is a SAGTA webinar and that we do encourage you to join SAGTA, become a member. This membership for the 2026 year will be 600 Rand or 300 Rand for students or retirees. And just remember that if you think about it, a daily coffee is anywhere between 35 to 45 Rand. And if you do the math over there, it's about 700 to 900 Rand a month on coffee. So rather have the saying of, I'll skip today's coffee and rather have a SAGTA membership, as there are just so many benefits of being a South African Geography Teachers Association member. So just to recap, in case you don't know what SAGTA is all about, we are a geography society where we do a lot of educational assessments or workshops, for geography teachers. And one of our most recent workshops that's coming up is through Cartosa, and that will be based on map skills and techniques for social sciences. This course has been submitted to SACE for endorsement. I think this is a really great course. I think I'm definitely going to join and get our department to go for a refresher. All of this can be done through bookings through our SAGTA website, so don't forget about that. More information will follow on through the course of the year. With regards to that, we also are very lucky, and I think being a geography teacher is something so special. I think people don't understand how lucky we are to have something such as Prep Share, and I'm sure Jackie will be very busy in the coming weeks and months to make sure that our Prep Share 2026 folder is up and running. But if you are a SAGTA member, you are very lucky to have access to other assessments set by teachers. You can share your assessments, and if you are a one-man department at your school, this is something that you can really hone on and get a lot of knowledge and just examples of some question papers. So that is just a few little things from the SAGTA team. Don't forget, sign up for your membership, join Prep Share, read the Georgia journal, and then lastly, don't forget about the map downloader. And especially with assessments now, if you are still setting assessments before the end of the year, use map downloader. It really is incredibly helpful. And then lastly, we will be having the SAGTA AGM in the coming weeks, and more information and dates will be shared with regards to this. But before we start today's webinar, I would just like to welcome Professor Jennifer Fitchett. And we are very, very honored to have her on our webinar today. And we're just going to do a short bio with all the amazing things that Jennifer has accomplished in her life and what she is busy with. So Professor Jennifer Fitchett is a professor of physical geography and the head of the postgrad studies and research development at the University of the Witwatersrand. For all of us past Witsies, we're very proud to have a Wits professor on site today. Her research is situated within the discipline of the biometeorology, exploring climate change and its impacts on plants, animals, and people. She has published over 100 papers on topics spanning contemporary and climatology, climate and tourism, climate and health, as well as plant numerology. We are so honored to have Jennifer Fitchett with us today. Welcome, Jennifer.
Thanks so much.
Not a problem. Are you able to share your screen? There we go.
I'm just waiting for it to pop up.
Just for our members, we are recording this session today, and once Jennifer has completed her presentation, there will be a Q&A session at the end. So you are welcome to have any questions and you can post them online. Over to you.
Perfect. Can you see my screen okay?
Yes, all perfect.
Awesome. Afternoon, everyone. It's lovely to be giving another seminar for SAGTA. I've done a couple of these over the years and presented at 2 of the previous SAGTA conferences. So some of you probably know me and some of you probably know some of this content. But it is indeed very timely. We've just seen the influence of La Nina on intensifying extreme weather impacts for those of us who were in Johannesburg and the broader Gauteng area over the past weekend. And if you are fortunately not in Gauteng at the moment, I'm sure you've heard about it on the news. So I'm going to start with a brief explainer of the El Niño Southern Oscillation, and we'll start with where it sits in terms of weather and climate scales. So we start down at the very, very fine scaled end of weather, where we're talking about hours, and we talk about something like a rain squall, through to days where we're talking about something like a tropical cyclone, and months where we're talking about the effects of a dry or wet season. And at that point, we pick up with the scale of climate variability that goes through months, years to decades. And then when we're talking about climate change, we're talking about trends over a period of 30 years or more. So our El Niño Southern Oscillation is located bang in the middle of that when we're talking about climate variability. It typically is a cycle that spans between 7 and 14 years, but in recent years, we've managed to move back and forth from El Niño to La Niñas and back in a much tighter time frame of just a couple of years. So it's what we'd refer to as one of the modes of climate variability. So how does this occur? At the equator, we have the meeting of the northern and southern Hadley cells at the intertropical convergence zone. Most of the air is therefore rising due to the very intensive heating at the equator due to the direct insolation, but also due to the convergence at the surface level through the 2 northern and southern Hadley cells. As a result of all of this air rising, we have very weak surface winds around the equator, and that's why it's a region that's referred to by people in the shipping industry as the doldrums. We also don't have any Coriolis effect at the equator. Coriolis is a function of latitude, and so that means that any remaining surface winds that we do have will blow almost directly from east to west. They're not going to be deflected towards the poles. So we then have our standard Walker cell conditions, where we've got these 2 northern and southern Hadley cells, the converging air, the very strong uplift, and a resultant low pressure system at the equator. We can then see this pattern of the due westerly wind movement. If we look at one of these plots, here we're looking at an aggregate of remote sensing wind direction. We've got this really, really intense equatorial flow, particularly across the Pacific Ocean. And so these east to west winds blow across the equatorial Pacific, and as they do so, they push water towards the western boundary of the Pacific Ocean. So that's as a result of the effect of friction. As the wind blows over water, those water particles are captured with the wind and accumulate up along the western boundary. The water quite literally piles up, which results in a much higher boundary sea surface level. It's about 0.5 to 0.75 meters higher than the eastern boundary. And due to that weight and the resultant pressure gradient, some of this water then flows back eastwards as an equatorial undercurrent called the Cromwell current. That That water then reaches the eastern boundary of the Pacific Ocean. It hits the continental mass and has therefore got nowhere other than to go than to move upwards. And so it upwells due to Ekman transport, which brings cold bottom water up to the surface. And so under normal conditions, this is what we're looking at. We've got our higher sea level across Australia. We've therefore got the undercurrent resulting in strong cold water upwelling just off the coast of South America. Where we've got cold water, we have a high pressure system and we've got subsidence. Where we've got the other side of the ocean, we've got our more tropical equatorial sea surface temperatures, and therefore we have a low pressure condition and rainfall. And then we've got our trade winds along the surface and a return wind up at the troposphere level. Now, there are very few maps that show the Pacific in one go. Usually the Pacific is sliced up into two pieces either side. So this map that's actually showing us all of our major plate tectonics is very valuable in terms of discussing the Enzo effect. So this is our normal conditions. We've got that high pressure off the coast of South America. We've got a low pressure off the coast of Australia, and we've got that air that's moving directly from east to west. So we then move on to El Nino. So not the focus of today, but important for context, because El Nino was discovered before its counterpart La Nina. It was first discovered in 1795 by fishermen in the Peru and Ecuadorian regions who recognized that there was a significant decrease in fish stocks every 7 to 10 years. They linked this lack of fish to a lack of nutrients, and we know now that nutrient levels in the ocean are controlled principally by the temperature of the water. And so this meant that something was happening to the water temperature. It was warmer, and it was therefore less suitable for the nutrients that these fish relied on. So what happens during an El Nino event? Our trade winds relax even further, so we have even more uplift. That means that less water piles up on the western boundary. That then means that there's less water that moves east as the Cromwell Current. There is therefore less water to upwell due to Ekman transport. And so your upwelling reduces. You don't have as much cold water coming to the surface. And so this area of warm equatorial water expands further and further east. As a result of that, our thermocline deepens and our pressure cells move west. So that's what it looks like during El Nino conditions. Our low pressure moves right to the center of the Pacific Ocean. We get the most amount of rainfall over the Pacific Ocean. And compared to that very, very hot sea surface temperature, we know that water stores about 4 times as much heat as land. We have comparative high pressure cells over Australia and South America. So again, looking at this tectonic map, because we can see Pacific all in one go, this is what we would be seeing across the Pacific. So the El Nino event then sets in motion what is termed the jerkness feedback. The trade winds weaken, upwelling slows down, and the Eastern Pacific warms. Because the Eastern Pacific is now warmer, it encourages even more uplift. Even more uplift means even less wind at the surface. So trade winds weaken even further. Because the trade winds have weakened, we've got less water being pushed across the ocean, upwelling slows down even further. And this becomes a never-ending loop until all of a sudden it changes. So if we're looking at a non-El Nino year, you can see that there's a really distinct blue tongue that stretches across here. That's your very cold upwelling water. And during an El Nino event, we don't have that blue tongue. We have this red area of very, very warm, 30 plus degree sea surface temperatures extending really far across the Pacific Ocean. So El Nino characteristics, they're a feature of the tropical Pacific, but there are similar phenomena in other oceans, such as the Indian Ocean dipole. Warmer water of South America advex eastward, and it occurs every 2 to 10 years. This is very outdated because I am recycling slides that I used at the SAGTA conference. It actually most recently occurred 3 years ago, and it is usually most pronounced during the austral summer. So another visualization of the difference between these, we can see November the 1st, 2015, compared to January the 1st, 2015, and how different those sea surface temperatures look across the equatorial region. We can also see changes in chlorophyll, and this is why it was of such importance to these fishermen, because things such as chlorophyll have a very strong response rate to our El Ninos. So what then is the Southern Oscillation? So that is the SO in ENSO. It's a measure of the variation in sea level atmospheric pressure across the equatorial Pacific Ocean. It's computed monthly using monthly air pressure anomalies between Tahiti and Darwin. And only in 1969 did the scientists make the connection between El Nino, which was identified as one particular system, and Southern Oscillation, which had until then been identified as a separate system altogether. And so today we measure the Southern Oscillation Index, and we can also measure the level of noise, and partitioning the two out, we're then able to get a sense of where we sit in terms of El Nino normal conditions and La Nina conditions. So if we go back to this diagram of an El Nino event, the N part now refers to what is going on with the ocean, with that undercurrent, with the change in the sea level and the upwelling. And the SO, Southern Oscillation, refers predominantly to what is happening in terms of our air pressure and measuring the difference between those high pressures over South America and Australia, or in the case of normal conditions, the low pressure over Australia and the high pressure over South America. So the focus of today is then La Nina. So La Nina is characterized by unusually cold conditions in the equatorial Pacific, and effectively it is an intensification of our normal Walker cell conditions, but a case where the trade winds get stronger. So we have lower amounts of uplift that allows more air to move along the surface. It's moving directly from east to west because of the absence of Coriolis. Our water is piling up to a much greater extent, creating a larger pressure gradient and a stronger Cromwell current. That Cromwell current then means that there is much stronger upwelling, and that strong upwelling brings a lot more cold water and nutrients up to the surface. And so during those conditions, the birds and fish thrive. So in essence, it's the opposite of El Nino conditions. So here we've got our very, very strong subsidence over South America. We've got our very, very strong uplift over Australia. We've got our stronger trade winds. And again, these systems self-intensify. So because we've got even stronger upwelling of cold water, that further intensifies our high pressure system. We've got all of our warm water located to a very small area right next to Australia. That's intensifying our low pressure. And our stronger trade winds continue that circulation. So this is then what we are looking at. That label is incorrect. I did this all in a big rush today, but this would be your La Nina conditions. So if we come back to the Southern Oscillation Index, we can identify an El Nino where you have a sustained Southern Oscillation Index of less than -8, and you've got a La Nina where you have a sustained Southern Oscillation Index of greater than 8. So if we look at this diagram, your reds tend towards an El Nino, but they would only be classified as an El Nino if we had sustained values below -8. And a La Nina is the blue category, but only when we have sustained values above +8. Anything between -8 and +8 is in your standard Walker cell conditions. This gives us a bit of a sense of what normal conditions look like versus what an El Nino condition looks like versus what a developing La Nina condition looks like. So then moving into Southern Africa, so this is looking across the whole world. Africa, what we can see is that there is quite a lot of variation in terms of how ENSO plays out globally. And the same applies for La Nina. And that's because we're not experiencing, for most of the world, a direct impact of the system. So it's only across the equatorial Pacific that we get the direct effects of how El Ninos and La Ninas play out. So you can see that across South America and then through to Australia. We've got the very wet conditions over Australia. We've got the very cool and dry conditions over South America, and cool conditions across the equatorial Pacific. Now that's a direct impact of ENSO because it's playing out there. Everywhere else in the world that we're seeing impacts of ENSO, it's through teleconnection. So it's either through our tricellular model, through our air transport, that we're carrying either colder or warmer air masses, wetter or drier air masses, away from this area to other parts of the world, or through the thermohaline circulation where our ocean currents are transporting again, either colder than usual or warmer than usual water masses across the world. So we're getting a secondary effect, but it is still one of the most dominant forces of climate variability across Southern Africa, as well as other regions of Africa, even though we are more remote from the Pacific Ocean. So if we look at South Africa, Southern Africa, including South Africa, Mozambique, Zimbabwe, areas of Botswana, and Madagascar, right the way north, experience cool and wet conditions typically during a La Nina. Just north of that, we get the opposite. We get dry conditions. And this diagram doesn't show it, but typically in the Southwestern Cape, we tend to get dry conditions in a La Nina. And we did have a relatively dry winter in the Western Cape compared to previous years. If we go off the west coast of Africa, again, we're seeing these cool conditions. The opposite roughly occurs during an El Nino event. So we can expect dry conditions over much of the interior of Southern Africa and wetter conditions in the Southwestern Cape. But you'll also notice that there are regions that aren't shaded at all, and those are regions that either do not have a direct influence of ENSO, or they have competing influences of other modes of variability that can serve to counteract those. Here in Southern Africa, you will get some years where, although it is a La Nina or an El Nino, we don't fully experience those effects. And again, that would be if we have counteracting effects from our more localized sources of variability, such as the Indian Ocean dipole or the Southern Annular Mode. So it's not a direct relationship nor an impact. We are quite far from the equatorial Pacific, and these impacts are translated via the teleconnections. They're impacted, counteracted, and enhancing more local influences. So the image I have in front of us is what we refer to as a tropical temperate trough. It extends from the Botswana low down to the Mascarene high. And the tropical temperate trough is responsible for the majority of our thunderstorms that we experience across the interior of South Africa during the summer months. Now, during a La Nina event, we have more frequent tropical temperate troughs. They move further south, and there is a lot more rainfall associated with these phenomena. And the reason why I'm showing you this image, and that's just a generic image I use whenever I'm talking about tropical temperate troughs, is because this is an image from what has happened the last couple of days. So here we've got that exact same pattern of a tropical temperate trough, and we've got those distinct areas where you can see from radar, we've got really, really high intensity storms that were occurring. Now, this explains in part the conditions that we had over Johannesburg and the rest of Gauteng over the last couple of days. So for those of you who are watching that, the South African Weather Service went right the way up to an orange level 9 warning. And it would be then the worst forecast storm in, I think, 100 years. It wasn't the worst storm that occurred, but it was the worst one that at the point of forecasting had been forecast. So it's a really intense storm. It's not the type of storms that we would typically have in an area such as Gauteng province. We would experience very severe storms more frequently along the coastline. And there were a number of projected impacts. They did then downgrade that to a level 6 warning, but there were some very severe impacts from the storm conditions over the last 2 days. A lot of damage in terms of destruction of trees, destruction of property, flooding through tunnels right the way across Gauteng province. So why did this happen? I'm going to take us back to the slide. For those of you who have a keen eye to what's happening down at the bottom of the slide, it had just about moved past, but we had a very unusual event where we had a tropical temperate trough and a cutoff low at the same time. And that really intensified what was happening through this tropical temperate trough. Now, cutoff lows also intensify during La Nina events. So during La Ninas, we typically have more cutoff lows and they tend to bear more rainfall. So we've got both of these systems interacting, and in this case, interacting at exactly the same time to create really, really intensive storm conditions. So if we're thinking about the impacts of La Nina, we need to be concerned about what it does, not only in terms of overall amounts of rainfall, but how quickly that rainfall occurs and the types of storm events that they're associated with. Because we're not just talking about gradually more rainfall occurring quite slowly across the full summer period, we're talking about these really intense storms that can occur. So then what are the future outlooks in terms of climate change? The IPCC Sixth Assessment Report of 2021, the physical science basis, firstly makes it very clear to us that ENSO is unlikely to go anywhere. These are systems that are not showing any shift under the climate models. We're not going to lose either side of it. So we're not losing El Niños and we're not losing La Niñas. But what we are seeing is that the intersections between ENSO and climate change and the strength of ENSO are very, very difficult to model and project. And with that, these changes in the fluctuation into and out of El Niño and La Niña events are a really challenging point in terms of climate modeling. And so this is a really big area of ongoing work by the IPCC authors, and all of the papers that they cite is in trying to resolve what the future is in terms of the cyclicity of ENSO, but also in terms of the associated impacts that we see with ENSO. We can also think more broadly. So there are a number of more global scale impacts. There are shifts in terms of the dynamics of tropical cyclones in regions, particularly in the Pacific, and those too are also intensified by climate change. And so we have all of these features that are playing into one another. So that brings me to the end. Thank you very much. Thank you for bearing with my slightly outdated slides. I had thought I'd caught everything, but clearly not. And I'm very happy to take as many questions as you'd like.
Thank you very much, Prof. That was incredibly interesting. And I think it was so interesting to hear about the current weather conditions that we've had, specifically in Gauteng. And especially it was the highest forecast in many, many years. Yeah, does anyone have any questions? I'm looking at the messages. I don't see anything. If anybody would like to turn on their camera or put on their microphone, you're welcome to do so now. Rita, I see you've put your hand up. You're welcome to ask a question.
Hi, can you hear me?
Yes, we can.
So what I want to know is how long do they think that the current La Nina cycle is still going to hold?
The projection is through the summer. So we typically look at El Niños and La Niñas in seasonal forecasts. Both systems tend to abate as we move into the austral winter. But it's very difficult to then forecast whether we'll have another La Nina the following summer. So right now, I'm not sure of any forecasters who have any degree of certainty in that regard.
Thanks.
Professor, just I have a question here. I'm just going to have to gather my thoughts. But when you have these forecasts of weather, uncertain weather experiences, such as flooding, etc., and obviously having a level 9, that was quite a high warning and an impact. What is the municipalities doing with regards to low-lying areas? They often say people need to be evacuated. And I know in our examinations, it's a very popular question to do buffering. But what is the government actually doing? Are they going out there and starting to evacuate people? I don't know if you have any information with regards to that. I'd be interested.
Yeah, it's a really good question. So, I mean, if we look across the regions that were flooded during this past weekend, it even extends beyond what we would typically consider as particularly flood-prone areas, so areas within a 100-year floodplain, for example. And even within that, I mean, we know how many informal settlements are located along our riverbanks. And there are times where there is government intervention, but it's usually not related only to flood risk. It's related to a number of different factors. So attempts to address safety, attempts to address fire, attempts to address service delivery. But unfortunately, I remember it being a question when I did high school geography. The ideal world where you have a buffer zone and you have an evacuation plan and you're able to think about how you would move all of these people out of an area, it's just not realistic in terms of the type of world that we live in. And it's not just a South Africa problem. It's not just an economically developing region problem. A really good example is Reunion Island, which is a French department located in the Indian Ocean. So they're owned by France. They have a lot of economic support from France. They had a tropical cyclone that made landfall earlier this year. And their attempts to evacuate, I mean, they can't evacuate off an island, but there were evacuation plans in place, and those weren't feasible to actually implement because you know just how many people are in a small area, how constrained road networks are at the best of times, and then you introduce flooding to them. So unfortunately, not enough. But it's also difficult to picture what would be enough, especially because extreme climate events are becoming more and more unpredictable. So we don't know what we're going to face. And often we don't know what we're going to face until a very short time period beforehand. And then the other side of it as well is that, for example, when we have a level 9 warning, and then it's downgraded to a level 6, that influences people's buy-in to weather forecasting and their level of trust to it. And the same goes when the opposite happens. If they under forecast, and then, for example, you get the Durban floods, again, people don't trust forecasting, and they're less likely to act at an individual level in response to a forecast that's been made. So we had the level 9 warning. It was very widely disseminated by the South African Weather Service, and yet there were a very large number of road accidents throughout Sunday morning. And those are people who are making a choice to be on the road. Now, some of them, that choice is more constrained than other people, but at the end of the day, those are people on the road despite a warning having been out.
Thank you so much. I see there is a question as well from Sarah Jane. She's put a question over here. She said, cutoff low, was it an upper atmosphere?
I'm seeing a question.
Perfect.
Okay, so yes, a cutoff low is an upper atmospheric feature, but I do know that cutoff lows in particular, the way that they're discussed by forecasters versus the way that they're discussed in terms of long-term climatology versus the way that they're discussed within school textbooks are very, very difficult. But the easiest way to think about them is they are quite a deep system. So to separate yourself out from talking upper or surface level, and rather just to think about them as the broken off piece of a mid-latitude cyclone.
Oh, brilliant. Thank you. Okay, that does help, because I always look at it and think, well, this looks nothing like we teach it. So I'm never too sure when they say, oh, this is a cutoff low. I look at it and I think, I'm so pleased that I'm not answering a question on that. Okay, but thanks for the clarity. Okay, we'll just so long as it's anything that's stopped from moving where it wants to move, we'll consider it a cutoff low.
Precisely. Okay. And the key component is that there was a mid-latitude cyclone that preceded it. So you wouldn't have a cutoff low just on its own. That's more likely to be a coastal low. So they are clearest to identify in the upper air because that's where the feature of the low pressure is most distinct, but they are deep systems.
Okay, thanks so much. Sorry, it wasn't an El Nino question. You mentioned it and I thought, oh, I just have to get a bit of clarity. Thanks.
Well, particularly because two happened at once, which is very unusual.
Yeah, perfect. Thanks.
We also have a hand. Can you, Sunny, if you want to ask your question?
Okay, thank you. I hope you can hear me from that side. Okay. My problem, okay, my network keeps buffering here, but I caught you when you were talking about the cutoff low. I wanted clarity on the cutoff low with its relationship to the La Nina or El Nino Southern Oscillation.
Yeah, so our cutoff lows that we experience in Southern Africa have a variability in their intensity and the amount of rainfall associated with them that is linked to whether we're in an El Nino or La Nina. So during a La Nina, we typically get a greater number of cutoff lows, and they tend to bear a larger amount of rainfall.
Okay, thank you. Okay, also, uh,
Yeah.
okay, also, according from my understanding is that they usually develop from the mid-latitude cyclone, and South Africa experiences normally is affected by the mid-latitude cyclone in winter. So I was left confused last week when I heard or saw that the extreme weather conditions, thunder, lightning, or unstable weather conditions that precipitate over the weekend is due to a cutoff flow system.
Yeah. Great question. So in the image that I
So
showed, you could
how
actually
did it
see the
develop?
bottom of that mid-latitude. Sorry, I was speaking over you there. So yes, you could see in that image I showed earlier, there was a mid-latitude cyclone that was passing just off the southern coast of South Africa. So mid-latitude cyclones occur year-round. During our winter, when our ITCZ is displaced northwards, with that, it brings our mid-latitude cyclones much further north. And so we have the majority of mid-latitude cyclones having an influence on the continental mass of Southern Africa, and particularly the Southwestern Cape, which is why we get a winter rainfall regime in the Southwestern Cape. When the ITCZ returns towards the equator by late September and then starts moving towards the Tropic of Capricorn as we move into November, it means that far fewer mid-latitude cyclones are going to extend as far north as Southern Africa, but there will still be a few that do. So every year, right the way through to November, even occasionally a few in December, will make passage that far north, that they have an influence on the subcontinent, but they don't become the dominant source of moisture, which is why the Western Cape tends to be dry during the summer months, but it's not completely dry. It will still get some rainfall events. And then when we get a cutoff low forming from that mid-latitude cyclone, those cutoff lows have very widespread impact in terms of the rainfall that they induce. And so again, we can have cutoff lows inducing snowfall in Lesotho right the way through until there are a couple of snowfalls once in a while in November even, and you can have rainfall across the interior.
Okay.
Thank you. Prof, we have another question. This is from Paula Oosthuizen.
Okay, thank you so much for that.
She says the textbooks state that the trade winds stop blowing, which then starts an El Nino. Can you go back to your slide and explain why the trade winds stop?
Yeah. Hi, Paula. They don't stop. So that's the quick answer. They don't stop. They weaken. So because you've got strong uplift, it reduces the amount of air. You've got very, very low pressure. You've got very little air along the surface. And so that means that there's very little air to be moving from east to west as trade winds. And then that sets in motion the Bjerknes effect. We don't know for sure which part triggers it. So trade winds weakening, or is it that we have a change in terms of upwelling and that changes the pressure systems, or is it that we have a slow warming of the Eastern Pacific? So I'll just reshare that slide. Sorry, I don't use Google Meet very often, so I'm just trying to find myself here. Can everyone see that?
Yes, we can. Thank you.
Does anyone? Okay, so this is this Bjerknes feedback. So we don't know precisely where it starts. The key hypothesis is that it is a weakening of the trade winds, and that weakening of the trade winds is because you've got stronger uplift at the ITCZ with the convergence of the two Hadley cells. But because that results in a slowdown of upwelling, that means a warmer sea surface, which in turn means more uplift, which in turn means that trade winds weaken. And that then means a warmer Pacific Ocean, which again means more uplift, which again means that the trade winds weaken. And so it isn't entirely possible to identify what that trigger point is, nor to identify how we move out of this locked in feedback loop to then move across to La Nina and that locked in feedback loop. So all of those are things that oceanographers are still exploring.
Perfect. Thank you very much. I don't see any other questions. Is there anybody else who would like to put their hand up and ask any questions?
I see Clinton's posted in the chat about textbooks being poorly written. It's really interesting, especially in climatology. It's really, really fascinating what has perpetuated in textbooks over very many years, no matter how many people try and engage with correcting them. And it makes it very difficult for geography teachers because it's from the textbooks that ultimately the matric exams are written. So you don't want to deviate off the textbook and then everyone gets their matric exam wrong. But equally, you don't want to then perpetuate information that's incorrect. So I really do know the challenge. And I know that Jessica Voyevich about a decade ago did some brilliant work looking at representation around climate change in the IPCC in the textbooks, but yet these issues continue.
So I think there's your challenge for 2026. The textbook of the year for geography teachers written by Professor Jennifer Fitchett. Co-written by
I wish
me.
I had the time. But even if I did, I mean, the unfortunate thing is that even if we were to write one, you're really fighting against the major publishing houses, and they have a very, very strong dominance over what goes into distribution. So sadly, I think it's a challenge for all of us.
Oh dear. I see we've got one last question here. It said, I heard you say Botswana low. Is that a some idea as opposed to a continental low? Nice question.
Yeah, so that's associated with the Congo air mass. So it's a feature we often don't hear a lot about because it's more influencing Central Africa. It is a low pressure cell that is not a fixed low pressure, so it comes and goes through convection, and it is a summertime feature. Yeah.
Okay. Can I just ask one more related to that? Sorry. But so, you're talking about taboos from textbooks, and for years we argued about a Kalahari high. Some of our students talk about the Kalahari high as opposed to being a continental high over the southern African continent. Is that incorrect, or is there still sort of an allowing of using of the term Kalahari high, or should we just refer to it as continental high, period, done, dusted?
So it's okay to call it a Kalahari high. Most of our fixed high pressure cells have dual names. So for example, our Indian Ocean high pressure is also called the Mascarene high, and both of those names are correct. So we can call it continental high or the Kalahari high. That's widely accepted to refer to the same thing. My bigger bugbear in terms of textbooks is the Mozambique current, because that technically doesn't exist. We have an Agulhas current that has eddies in the Mozambique channel, but we don't have a Mozambique current. So there, I mean, again, people would know what you're talking about, but when you get into the nitty-gritty of oceanography and what actually constitutes a current, it's not really a current in the same way that there's a difference between an ocean and a sea in terms of scale.
Quite a big one.
But Kalahari high is...
Okay, all right, no, that's perfect. Thank you so much. I just wanted sort of clarity. So for years at SENS, so everybody knows this, as St. Stithians, we weren't allowed to use the term Kalahari high, and it's sort of crept back in since there's been changes, but it's quite interesting. I still wonder whether we're making it a mistake by calling it Kalahari high. So, okay, perfect. Thank you. Taboo settled. We will allow the boys to call it. Thank you for that. That's great.
They could go overboard and call it a continental Kalahari high pressure and tick all the boxes.
Then I'll be supremely impressed and I'll give them the mark. Thank you so much. That's great.
Perfect. Well, I think there's no more questions in our box, and I don't see any more hands. So just on behalf of SAGTA, Professor Jennifer Fitchett, we would just like to say a huge thank you for leading today's insightful session. We really do appreciate your time, the care and the depth that you've brought to the session, as well as answering many different questions on different topics, which I think is something that a lot of teachers have, but perhaps there's never a platform that these questions can be answered. So thank you so much for sharing your knowledge, and we're just truly grateful. And just a round of applause from all the SAGTA members and everybody on today's call. Thank you very much. As well as thank you to all of our participants who have joined today. It is wonderful to see some of our followers who have been on most of our webinars this year. I wish you all the very best for the last push of the year. And matric marking, for those of you who are going to marking, I hope you have a wonderful networking and enrichment time during marking, and hopefully energy finds you during that time. To those of you that are going away for the December break, I hope you have a safe trip. And for some of us that are going to be staying at home, I hope that you perhaps enjoy some of the rain that we might have, and that our gardens blossom. So over and out from SAGTA, may it be a wonderful festive break for you, and we are looking forward to a wonderful 2026 year with many, many more webinars and different topics. Have a wonderful afternoon, everyone. Bye.